Hello, everyone. My name is Mascaran, and in this video, we are going to discuss PN junctions. This is not an introductory video, it's more of a quick review. So if you're not familiar with PN junctions, I would suggest to look at some of the more introductory material on PN junctions, either on YouTube or just online anywhere. This is meant to be a quick summary, so I'm kind of assuming that you already know about PN junctions, and this is just like a summary style video. So, okay, let's get started. We know that silicon is an element in the fourth group of the periodic table. And what that basically means is that each silicon atom has four valence electrons, right? And so that also means that each silicon atom can form a covalent bond with four other silicon atoms by sharing electrons in its valence shell. So here I have shown an example where there's a silicon atom in the red, and this is, let's say, one silicon atom forms a bond with another silicon atom using one of the electrons in each of their covalent in each of their valence shells. So this is like bond number one, this is bond number two, and that's bond number three, and that's bond number four. So that's like each silicon. So that's what I meant. Like each silicon atom can form a covalent bond with four other silicon atoms, and so you can sort of you might have seen this written um, in in some of your chemistry classes. So this is basically yeah, this is basically representing the covalent bonds of silicon atoms in a crystal. So essentially, like if you repeat this pattern of each silicon atom sharing bonds with four other silicon atoms, and if you keep repeating the geometry and it expands, that basically forms a silicon crystal, right? But here's the thing. Silicon crystals by themselves are not very interesting. So one interesting thing you could do with a silicon crystal is that you can dope it. You can dope a silicon crystal with to make it a p-type or an n-type material. So here's an example. Silicon is in the fourth group of the periodic table, right? You could take another element, let's say boron, which is in the third group of the periodic table, meaning that boron only has three valence electrons. And so if boron is introduced or doped into a silicon crystal, then it will form a hole because it can only form three bonds, and then there would be like a lack of an electron um, in the fourth place. And so when boron is introduced into a silicon crystal, you would have an absence of an electron, which is basically a hole, like I showed here. So you could do the exact opposite thing. You could basically dope a silicon crystal with not a third group element, but a fifth group element. So let's say phosphorus. So phosphorus, because it's in the fifth group of the periodic table, then that means that a phosphorus atom will have five electrons in its valence shell. And so when phosphorus atoms are introduced into a silicon crystal, that would mean that every time phosphorus forms bonds with the nearby silicon atoms, there would be one free electron um, in that scenario. And so that's the situation on the right here. So you have one free electron when a silicon crystal is doped with a fifth group element such as phosphorus. So these doping scenarios also have names. So the one on the left is called um, a p-type or an acceptor doped material, and the one on the right is called the n-type or the donor doped material. Okay, so this shouldn't be new knowledge, right? This is something that you would already know. And yeah, like I said, p-type material has free holes, and n-type material has free electrons. Now, here's a quick representation of a p-n junction. Here, I've shown some charges in black and some charges in red. So here's the important part. For example, in the p-type material on the left here, you have free electrons. So let me just mention that. So these are free, free holes, my bad. These are free holes. And then there's also some charges in the black. So those are fixed negative charges. So that's important to note. These are fixed. And these are not, this is different from free holes or just like free. Basically, it's that means it's mobile. Those charges can move, the ones in the red. But the ones in the black, like the fixed negative charges in the p-type material, they can't move. They're fixed, right? And so it's a similar concept for the other side as well, the n-type material. So here we have free electrons or mobile electrons. But then there's also fixed positive charges. And I emphasize that the fixed part because it's gonna play a part later on. So just bear with me for a moment there. Okay, so then in a p-n junction at time zero, let's say when these two when there's a p-type material and an n-type material right next to each other at time zero, let's say, and what happens, right? So essentially, you have free electrons in the n material, and you have free holes in the p-type material. So what's a hole, right? Hole is not a particle; it's just an absence of an electron. So it's only natural that electrons will want to move towards wherever there's lack of electrons. So in other words, electrons and holes attract each other, right? And so that's what's going to happen here. These electrons are going to diffuse towards the holes, or basically the holes and electrons diffuse here at time zero, and there's a diffusion region formed like shown in this part here, right? So, a depletion region. So here in this region, basically all the electrons and holes have diffused, and there would be some sort of diffusion current. This diffusion, however, does not last forever. Basically, what happens is once enough electrons have diffused towards the p region, there's also negative charges, the fixed negative charges in the p region here. So let's say these fixed negative charges, they are going to repel any further electrons that are trying to come or trying to diffuse into the p region. So that basically means that after a while, there's some sort of a limit, there's some sort of an equilibrium that will form, and this diffusion will not continue forever. And so, yeah, so that's the depletion region. And it's important to note that in the depletion region, there may not be free holes or electrons, but there's still fixed charges. So there's fixed charges, fixed positive charges here, and there's fixed negative charges here. And I emphasize that because of these fixed charges in the depletion region, there's an electric field, right, from the positive to the negative. So this is the electric field of a p-n junction. And so anyway, this is like this representation is also equivalent to like something that we see in electronic schematics all the time. You know, a common symbol for a diode, which is a p-n junction. So this is like the p side, and this is the n side, and it's also called the anode and the cathode. Again, not new knowledge. This is something just reviewing really quickly. And so, yeah, another thing is the potential difference of the p-n junction. So that's VD, and it depends on the thermal voltage. So that's VT here. And the natural log of the acceptor concentration, the donor concentration, and the intrinsic concentration, and the intrinsic area concentration. Yeah, or the square of that. Yeah. So VT here is basically the thermal voltage. So this is the thermal voltage, and thermal voltage for obvious reasons because it depends on temperature. Here it depends on KT. Basically, the expression is KT over Q. Yeah, and so K is basically the Boltzmann constant. T is the absolute temperature in Kelvin, and Q is the charge of an electron. So K and Q are constants, right? Something that you can find the value of on the internet. The only real value variable here is the temperature, the absolute temperature. And so that's why it's called the thermal voltage, because everything else is constant. It just depends on the temperature. Um, so it's called the VT, the thermal voltage. One thing to note here, though, is anybody who's taking any MOSFET courses or working or has some analog design knowledge, there's also another variable called VT, which is the threshold voltage of the MOSFET. And I just wanted to say that that VT is not the same as this VT. So those are two different things. That's the thermal. What we're talking about is the thermal voltage, and something else is the threshold voltage of the MOSFET. These are, even though their letters are the same, it's just two very different things. And so yeah, the thermal voltage is around 26 millivolts at 300 Kelvin. Okay, let me see here. Yeah, I think I discussed everything here. So here's another interesting thing, an interesting experiment. What happens when you connect this PN junction to, let's say, a battery, right? Something that we do frequently, or you would see frequently in electronics, right? We use diodes or PN junctions for different kinds of reasons. So what happens when you connect a PN junction to a battery? Um, Now, can you, to start off with, one thing is, what is the direction of the electric field in the depletion region? So if you remember, there's fixed positive charges in the N region, and there's fixed negative charges in the P region, right? And also in the depletion region. And so the electric field of the PN junction is in this direction. Now, the electric field of the battery is obviously in this direction, right? And so let me write this in another way. Let me move this upwards here. So you can see here, the electric field of the battery is basically in the opposite direction of the electric field of the PN junction. And so if the electric field of the battery is large enough, it will essentially counteract or overcome the electric field of the PN junction, in which case current starts flowing through the diode or the PN junction, right? And this is typically, like, very typically called forward biased diode, right? Because current is flowing, right? And another thing to note here is when the diode or the PN junction is forward biased, the depletion region becomes thinner. And the opposite happens when you change the polarity of the battery, right? So in this case, the electric field of the PN junction is this way, and the electric field of the battery is the same way. And so essentially what it's doing is that it makes the depletion region thicker, and it basically increases the barrier. So it's even harder to pass current, and so no current will pass. And this is typically called a reverse biased configuration. Again, I'm moving quick here, and I might not be discussing all the details because this is like a quick review video. There's interesting details about why the depletion region becomes thinner or thicker with these voltage changes, and or with reverse polarity. And yeah, again, something that should be understood, and you would find it in some introductory videos for range of things. All right, so last thing before I finish off this video is you could like some of the uses or appearances of PN junctions in analog IC design. Maybe I shouldn't say like consequences. I just say like uses. Yeah, for lack of a better term. It's just what I just want to say is like there's some parts of design where we actively use p-n junctions, and other parts where p-n junctions are formed parasitically. So one example is latchup. Here, what happens is if there's a PMOS and an NMOS close up to each other, for example, in an inverter, what happens is you would have these parasitic PNPs and NPNs that are formed, and under the right circumstances, the current will start to leak to these parasitics. And so that's basically called a latch up. And there's, I think there's checks for that while you're doing layout. So something that we don't want and we want to get rid of is latch up. And it's caused due to these unwanted p-n junctions in our design. One other place where we make use of p-n junction is reactor. So if, let's say, you're designing a VCO, you want variable capacitances, you could use a p-n junction. The reason for that is, again, like I said, depending on the potential across the diode, the depletion region width can change, right? And so if you look at the geometry of this p-n junction, it's very much like a capacitor, right? It's just like two plates of metal with opposing charges and with some dielectric in between. And so you can imagine if this depletion region is changing, the capacitance is also changing, right? And so by varying the potential across a diode or a p-n junction, you could vary the capacitance of a diode. And so so that's a variable capacitor, and you could use that to your advantage in CMOS designs. Like again, if you want a variable capacitance somewhere, very common in a VCO. So you could use a reactor there. Reactors can also be made with like MOSFETs and stuff, but that's something I'll leave to a later video. But yeah, that's pretty much it for this video, and thank you so much for watching. I'll see you in the next one. Bye-bye.